Okay, this is lecture number 13, and in lecture number 12 we have seen different applications of scalar triple product. One more application which is remaining is the coplanarity of two lines. What should be the condition so that we say that R is equal to A plus TB and R is equal to C plus PD are coplanar. So we have been given two lines, R is equal to A plus TB and R is equal to C plus PD. Then suppose we want to write down equation of a plane which contains this particular line is R minus A vector in that plane must be perpendicular to B cross D, should be equal to 0. Okay, so equation of plane which contains this line is going to be this. Now I have written it quickly, but have you really understood it? Now there is a plane which, say for example this plane, this is for some other application. Suppose this is the plane and R is equal to A plus TB is the line in that plane, and I want to write down equation of this plane. Then now R is any point in this plane. R is position vector of any point in this plane. Then R minus A vector R minus A should be perpendicular to B cross D. What is B cross D? Now this vector in this direction is B, along the line is B, vector in this direction along this line is D. This is vector B, this is vector D. And now you want a perpendicular to both B and D. That is where the application of cross product is. So if we consider B cross D, that is what is going to be the vector perpendicular to B as well as D. So this vector is B cross D. So B cross D is supposed to be perpendicular to R minus A. That gives me the equation of plane, and that product is 0. So if I simplify this, I get R dot B cross D is equal to A dot B cross D. So box RBD is equal to box ABD. So this is what is the equation of this plane containing this line. Now we want this line to be coplanar with that. So do we have any point on this line? Yes, we have a point C. So condition for coplanarity of two lines is going to be this. R is any general point, should be, we should put C in place of R. So CBD, if it is equal to ABD, then these two lines are going to be coplanar. That is what is the condition. So C and A are in the same plane, and their corresponding dot product with B cross D creates exactly the same volume. That is what is the condition for two lines to be coplanar. Now next is finding out the shortest distance between the skew lines. Now if two lines are intersecting, the shortest distance is going to be 0. If two lines are parallel, then finding the distance between them is also going to be relatively easy. Maybe we will derive that formula also later. But the most complicated thing amongst all is, in space you have two lines which are not parallel, not intersecting, and they are called skew lines. They don't intersect, they have a gap in between. And maybe you can visualize this picture as three-dimensional picture. There is this line is R is equal to A plus TB, this line is R is equal to C plus PD, and I have drawn two planes which are containing that line. Actually there could be infinitely many planes, but the planes which I have drawn are such that they are perpendicular. Both the planes are perpendicular to the shortest distance line. The shortest distance is going to be perpendicular. We need to intuitively understand this. If we have two skew lines, then the shortest distance will be the perpendicular. So that is what I have shown. Vector or segment LM is the shortest segment amongst them, and we have point A here, we have point C here, and now we are supposed to find out the shortest distance. You pause the video, check if you can find out the shortest distance yourself, else look at the solution. Now vector AC that we have, vector AC is any point on the first line and any point on the second line which is joining that, and vector LM that we have right now here is definitely perpendicular. So LM is along B cross D. That is what we have already seen. So okay. So now the mechanism that we are going to do here is, suppose if we shift this particular vector keeping it parallel and A and L coincident, if we make A and L coincident, then what will happen? Basically, we are taking this vector AC and moving it along, keeping it parallel to the line. A goes to L, and therefore vector AC becomes LD. Now, is CD going to be in the same plane, in this plane? Yes, it is not going to. CD will be contained in this plane, correct? So this is going to be a parallelogram. Now what we are going to visualize is, now L is coterminal, LM and LD both have the same initial point, and now this LD vector which we have, if we take projection on LM, that is what is going to be our shortest distance. The projection of LD on vector LM, which is B cross D, and that is what is going to be distance LM. Now in this case what we should do is, while taking the projection, the vector B cross D must be unit vector. Therefore let us write down what is the distance LM. Distance LM, or maybe distance LM, is going to be projection of vector LD on B cross D. Vector LD is C minus A dot B cross D. This is what is the projection, and we have B cross D, so that we make it unit, and that is how we are supposed to get the distance. And now this particular box product can be negative, and we want distance to be always positive. Therefore this is how we find out distance between skew lines. It is one step. If we understand what do we mean by projection, this transformation of vector AC to LD needs some three-dimensional imagination for you to do. If you understand that well, then projection of LD on vector perpendicular to B and D, which is B cross D, it has to be unit vector. Otherwise unnecessarily this distance will be multiplied by some scalar, because projection, when you are taking the project on which you are taking the projection, the vector, if it is unit vector, then you get the length of projection. So LM is equal to C minus A, that is this vector, taken dot product with B cross D, made it unit vector. Hope you have understood this. Now okay, distance LM, and if you expand this, you can express this in terms of box CBD minus box ABD. Okay, line of intersection of these two planes, intersection of the planes through the given line and LM. So what is going to be the line of intersection? So what is the equation of plane which contains LM and AL. LM and AL. Equation of plane which contains LM and AL. Can we find out the equation of that plane? It will be R minus A, that is the vector, dot B cross D R minus A dot B cross D is equal to 0 is going to be the equation of plane containing LM and AL. LM and AL. Any point in that plane, R minus A you are taking, and its dot product with B cross D should be 0. B cross D is a vector which is perpendicular to B and perpendicular to LM. Right? Then this vector, which is going to be normal vector to the required plane, if taken dot product with R minus A, you should get 0. So the plane containing line AL and LM is this, and the plane containing line LM and line CM is going to be R minus C dot D cross B cross D is equal to 0. So the line of intersection of these two planes is going to be the line LM, equation of line LM. So this is what is important, shortest distance, etc. So let us get into solving couple of problems. First problem is, show that the plane through each of the edges of a trihedral angle bisecting the internal angle between other two are coaxial. Now this is something similar, analogous to concurrency of angle bisectors in triangle. The angle bisectors of any triangle, they are concurrent at I. It is a two-dimensional picture, therefore I is the in center, that is a point, which is point of concurrency. In this problem, what we are asked to do is show that the planes through each of the three edges of a trihedral angle bisecting the internal angle between the remaining two are coaxial. Okay, so let me quickly draw the diagram and explain you what is this problem and how to solve it. Okay, now you have to visualize this picture three-dimensionally. So it is actually, I have drawn a tetrahedron with three edges, OA, OB and OC. Okay, and now what this problem all about is, if we consider say edge OA and angle between these two planes. Which two planes? OAC and OAB. The angle between these two planes, if we consider, and if we consider a plane passing through, bisecting that angle and passing through OA, suppose we consider this plane, and if we consider one more plane, say bisecting angle between OAC and OBC, then suppose you consider this plane which is bisecting the angle between OAC and OBC, then the third angle bisecting plane also if you consider, first of all, if I get these two planes, then I will get a line of intersection, and that line of intersection is going to be this. I am trying to draw it as clean as possible so that you understand the three-dimensional view behind it. Now this is one angle bisecting plane, this is another angle bisecting plane, and the problem is if you happen to draw the third angle bisecting plane, then it is also going to pass through this line. That is what is the problem. Now to solve this problem, let us take, because it is not given, let us take OA, OB, OC unit vectors. Okay, so what is the advantage of taking them unit vector is, suppose this is OA and this is OB, OA and OB, then if I complete this rhombus, then I get the vector which is A plus B. This is A, this is B. Vector A plus B, if it is a rhombus, then it is angle bisecting vector. That is the advantage that I have here. Instead of getting into equations of angle bisecting planes, I am going to use this fact, this property of rhombus here, that A plus B vector is going to be internal angle bisector of OA and OB. Okay, so now I have to write down the equations of these planes. So first plane, let us take plane passing through OA and bisecting angle between OAC and OAB. Okay, so I have one vector R, I have one vector, and I need a vector perpendicular to the required plane. I need to generate a vector which is perpendicular to required plane, and it is also supposed to be perpendicular to vector A. So the perpendicular vector is going to be A dot B cross C, sorry, B plus C. A cross B plus C. A cross B plus C is going to be the vector which is perpendicular to required plane and any point R minus 0. So R dot A cross B plus C is equal to 0 is going to be equation of this plane. Okay, what is going to be the equation of the second plane which I have drawn here? This plane R dot, this is C cross A plus B is equal to 0, and by symmetry we can write the equation of third plane as B cross B plus C, B plus C, B C plus A, C plus A is equal to 0. So these are the three planes, angle bisecting plane containing the remaining edge, that we have found out now. So these are the three planes. Okay, and now these three planes have a common point. So all these planes are passing through origin, therefore they have a common point. And if three planes have a common point, and if suppose we want to prove them coaxial, that means now it is like pages of your notebook. Suppose these are the planes which are coaxial with this is a common line. Then what is important here is, if we draw perpendiculars to these planes, suppose I draw perpendicular to this plane, perpendicular to this plane, perpendicular to this plane. So perpendiculars drawn to all the planes which are coaxial are going to be coplanar. The vectors which are going to be normal vectors of all of them are going to be in the same plane. And therefore, if we can prove that the normal vectors of these three planes are coplanar, then they are coaxial planes, right? So we have a normal vector A cross B plus C, we have a normal vector C cross A plus B, and we have a normal vector B cross C plus A, and you will be surprised to know that the C cross B plus A plus B cross A plus C is anyway, this identity itself is 0. If you observe, A cross B you have and B cross A you have, A cross C you have and C cross A you have, then and the remaining B cross A you have, B cross A you have. All those cancel out, and therefore this is anyway 0, and therefore these three normal vectors are coplanar. Why they are coplanar? Because one is linear combination of the other. You can express one vector as a linear combination of remaining two, so therefore they are coplanar, and this identity is true, and hence we have shown that these three angle bisecting planes which contain the third edge are coaxial. Now the second part of the problem is to find out the common line in terms of the vectors along the edges. So we are supposed to find out the equation of the common line. Now the perpendicular, if you choose any two of them, they are perpendicular to the plane, and the line, black line that we have is going to be perpendicular to both of them. So what we should deal with now is A cross B plus C cross C cross A plus B is the vector which is going to be your vector with the direction of the black line, and the base point anyway you have origin. So this is what is the vector, and maybe k times vector is equal to 0 is going to be the line. This is what is going to be your line, the line of intersection of this plane. R is equal to not equal to 0. I mean, this is the vector. Let us find out the vector first. What is this vector? This vector is A cross B plus A cross C cross C cross A plus C cross B. Now if we distribute cross, then A cross B cross C cross A plus A cross B cross C cross B plus A cross C cross C cross A plus A cross C cross C cross B is equal to. Now every time we have to use the vector triple product, so this goes here with the dot product. Now I am doing it little fast. C cross A goes to place of B and it becomes a dot product, but A dot C cross A is going to be 0, therefore we need not have to worry. Then this goes over here and we get it as C cross A dot B. That is what we get here, and then A comes out. That is what with negative sign. First term gets cancelled if you understand it. Now second term, this goes here, therefore I get plus A dot C cross B, A dot C A B Okay, A dot C cross B times B, and if I put it back here, it is going to be 0. If this goes here, it is 0. If this goes here, again it is 0. If this goes here, then plus A dot C cross B times A, and then it is 0. So the only ACB, the negative sign is not in the order, and therefore I can make it minus sign, I can absorb in this bracket, and then it becomes ACB. So maybe with some correction, I know it is ABC times A plus B plus C. So this is what is the cross product of this, and this is the vector, scalar times vector along this, and therefore equation of this line is going to be R is equal to 0 plus T times A plus B plus C. That is what is going to be the equation of the line. I am aware that whatever I have done through video lecture etc., it is going to be difficult for you to really understand and digest, but you have to take your time. You have got the notes with you, that is what precisely is written in the notes. Spend time, try to understand. If you still have problems, you can always contact us. This is what is lecture number 13. We stop at that point and look at some other different things in lecture number 14. Thank you.